All right. Hi, everybody. If you didn't figure it out by now, I did enter curved test scores earlier today. So those are into my learning. Yes, that is included. So it's all added together into one aggregate score. I'll pass you back the individual papers. I have one student that hasn't done it yet. Okay. It's not going to do his last work, so. I know, but that's. Yeah, maybe after class or something. Okay. Sure, if you want to take a look at it, I'm okay with that. All right, today, 2 sections. I know. But real talk here, folks. We're a little behind with where I'd like to be, which is fine. Like, there's places where we can catch up in second semester. It's fine. There's things in second semester I like to do that I don't have to do. There's some buffer at the end that is typically review time that we lose a day or 2 off of that. It's not the end of the world. But just letting you know that we're gonna cut some things that I would call consider enrichment. That aren't necessarily is not an AP expectation, but I think is good to see that we're going to lose a little bit of that stuff here in an effort to kind of get back on pace, which is fine, right? Everybody's okay? Just real talk, telling you where we're at, because I'm going to do that a couple times today inside of this lesson, skip some stuff that I would normally like to do. Okay? All right. So today. Really, I should say all of chapter 4, the book chapter 4, is about applications of derivatives, right? We've built out this tool, the derivative. We've learned how to take the derivatives of all sorts of functions. We've done the quotient and product and chain rules. We've looked at individual derivative rules for polynomials and power functions, and exponentials and logarithms and trigs and inverse trigs. All these different function types that we've seen before, we've now learned how to take the derivative of. We're going to now look at what can I do with that as a tool. So today, the first part, what we're going to be doing is using that derivative to analyze functions. So what can I learn about a function by using its derivative? No.
I'm sorry, I probably should have asked before we start the lesson, but
okay.
Are we going to have a chapter 4 test, or is it just going to get
You're just going to stick it up. There's not enough time before. You guys don't want another test. No, we don't. I am anti mini exam week before the real exam week. I think that's dumb. So that's what we're going to do. As I'll teach right up. Maybe have the class period before the final, but I'm going to just teach up to the final. If that works for you guys. We'll talk about exam format when we get back from break. Nobody wants to hear that right now. Right.
We really only have 2 full weeks of school in finals.
I think that's right. All right. So in section 4.1, we're going to learn about the relationship between minima and maxima for a function and the derivative. Okay? So there's 2 different types of maxima, and of those, 2 different types of extrema, minimums and maximums, right? And then for minimums and maximums, there's 2 different types of those. There's local and global, or our textbook says absolute. You could use the term global interchangeably. So absolute maximum says that you just have some y-coordinate that's equal to or higher than every other y-coordinate in the function, right? And the minimum is just the reverse. It's less than or equal to all other y-coordinates in the function. Can you have more than one absolute min or max? Yes, because you can have ties for first, right? The sine function has infinitely many maxima or minima because the maximum value is 1, and that happens infinitely many times, right? Or the minimum value is 1, and that happens infinitely many times. Is everybody okay with that? Do you have to have a absolute maximum or minimum in your function? No, why not?
Because you just have global ones.
That's the global. What if,
Oh,
can you have no global or absolute maximum or minimum? Sure, so like Sarah says, what about a linear function that just goes on forever in both directions? There's no highest and lowest point on that, right? Is everybody okay? You could get the same effect if you have like a line segment with open circles at the end, right? They're not going on forever, but you can get infinitely close to whatever that open circle is, but never get there, right? That has no absolute minimum or maximum. So those are the two cases where you have like an arrow going up or down forever, or an open circle at an end, where that's where the lowest or highest point is at an open circle. Does everybody feel okay there? And then you have local maximum or minimum, which just says I can find some open interval, and inside that open interval, there's a highest or lowest y coordinate inside that open interval. Not closed, but open. Because the endpoints don't count. Right? So if I took a linear function, if I took an open interval there, there's no maximum or local maximum or minimum there, because the endpoints, if it's open, are open circles, right? But if I had like, some quadrant or some polynomial function that does like this, but has a bunch of bumps in between, I can take an open interval with one of those bumps in it. That would be like a local maximum or local minimum. Everybody's okay with that? And you've talked about this before in classes, right? You guys still remember how to use your calculator to find maximum or minimum? Just by using the graphing and do the min and max command, like second trace, right? We're going to learn how to do this now algebraically, using calculus as our tool to find those maximum and minimum. Does everybody feel good so far? All right. So let's look at an example. So this is the function y equals 3x to the fourth minus 16x cubed plus 18x squared. And it's defined on the interval from -1 to 4. So this is on a closed interval because they're or equal to values on the domain, right? So if I look at this, the I don't want to use this guy. The absolute maximum is not 1,5. Yeah, so this is where the absolute maximum is, right? It's the highest y coordinate on the whole thing. Because it's a closed dot, we can use it. Yes, 100%. The absolute minimum is 3, -27. And your local max, any local maximums? 1,5 is the only local maximum. The endpoints can't be local because of the way that it's defined. This has to be an open interval, and I can't pick something over here next to it, right? How about local minimum? This guy's also local. Again, I can pick a closed interval around it, and it's the lowest point on that closed interval. So absolute extrema can be local, right? If they're not an endpoint. Sarah?
Why is that point at 0 not a local minimum?
Oh, it is. Goodness gracious. Thank you.
Why does it have a dot like the 1,5?
I don't know.
Okay.
Maybe I did a bad job.
So that's another local?
Yes. Yes. Does that feel good? Okay. Again, should be largely review, right? We're just kind of like smoothing out a couple of the finer points about how like the endpoint can't be a local. But otherwise, this is very much like I know when I see it. We talked about this in a couple of classes. I should feel pretty comfortable here. Yes? Okay. Oops. All right. Important theorem. the extreme value theorem. This is one, much like the intermediate value theorem, that you'll need to know by name. You'll have to have it memorized well enough to where you can use it and quote it inside of your work. So what the extreme value theorem says is if you have a continuous function on a closed interval, you need two things. Continuous function on a closed interval. Then the extreme value theorem states that somewhere on that interval, the function attains at least one absolute maximum and absolute minimum. Okay? Continuous and closed is the requirement. EVT, we'll abbreviate it just like we did the IVT. The EVT, extreme value theorem, states the function attains at least one maximum, absolute maximum, and at least one absolute minimum. Rather than proving this, I'm going to demonstrate why this is true. So here's my closed interval from A to B. If I try to connect the points without picking up my pencil, I had to create a maximum and a minimum, right? What if I do this? And it's like, oh, look, I connected them. Well, so I have a minimum and a maximum, right? The endpoint becomes my absolute minimum, right? Or if I try to I'll put them at the same level and then, oh, look, right? No matter how I draw this, if I draw a straight line, they're all maximums and minimums, right? Every point on the line, all right, I get it, Mr. Blue. Can't do it. I want to point out to you with these next two pictures why the closed interval is important. If I look at this graph, this is not continuous, right? Is there an absolute maximum? This is open. Is there an absolute maximum? No, right? Because the function can creep as close as I want to that open circle, but I can never actually get there. So I can always find one point that's just a little bit higher, like incrementally higher, right? So if I lose continuity, something like this could happen. I'm not guaranteed an absolute maximum, right? Do I have an absolute minimum? Yeah, sure. On my closed interval. If I don't have a closed interval, does this have an absolute minimum? No, because it's an open circle. Does it have an absolute maximum? No, because the function's going up forever. So if I lose any part of the closure, I can also draw something that has no absolute min or max on it. Okay, so that's why you need those two conditions. The continuity prevents something like the first case, the closed interval prevents something like the second case. Everybody cool? Fermat's theorem would not need to quote this by name. It's not a one that you use to do a problem on the AP exam by name, so this is not a you need to memorize this form or theorem. But it is important. It says that if f has a local maximum or minimum at C, and if f prime exists, then the derivative of f at C is 0. Notice that it says local minimum or maximum. Why does it need to be local?
Oh, because then it's just like a little new, like there's an endpoint.
Because this would be an absolute maximum, right? What's the derivative going to be at this value?
1.
Yeah. Doesn't exist because there's no left-hand limit for it. Remember, a derivative is really a limit of the slope function, right? So that's why it has to be locals. And why can't I just say that, and I mean, like, won't my, like my guys just look like this? Why do I need it to exist? Why can't I just say the derivative is going to be 0?
Because if the derivative doesn't, like, what was the question?
Why? Well, it has this condition that, has a local maximum or minimum, and if the derivative exists, then the derivative is 0 at those.
It needs to be local minimum or maximum, because then it's like.
No, I'm talking about the existence.
Oh,
Like,
okay.
why is that an extra qualifier in there? Why would the slope, why would the derivative be anything other than 0 at a local maximum or minimum?
You want.
It can be. What if my graph looked like this?
Oh, that's fine.
Those are local maximums and minima, right? What's the derivative at those values? Undefined, because it's a corner, right? Everybody remember that? So far, so good? Okay, so that's why we have this extra qualification, because the derivative here is not going to be 0. Doesn't exist. Provided the derivative exists, though, the absolute minimum max is going to have the derivative will be 0 there. No.
So at those corners, would they not be considered local minimum?
No, they absolutely are still local minimum and maximum, but the derivative doesn't exist there.
Okay.
Cool. Question. Can I do this in reverse?
Yes.
Does it, if I have a place where the derivative is 0, or where the derivative fails to exist, does that guarantee me a local minimum or maximum? No, right? So the fails to exist part should be easy, right? Like derivative is going to fail to exist there. Everybody agree? Why?
Left to right hand limits to agree.
Yeah, it's a discontinuity or the left-hand, right-hand limits won't agree. Sure. I think in this case they actually would both agree, but it's still a discontinuity, right? They're both going to 0. But it's not continuous, right? You can't have differentiability if you don't have continuity. That's a requirement. But that's not a absolute maximum or minimum, right? Everybody agree? Okay. Okay. But if the derivative is 0 there, that's got to be a max or min, right? Is that true? No, right? What could we do? What about a graph like that? The slope is 0 there. Is that a max or min though? No. So it doesn't work in reverse. But here's the good news, is that anything that is a local maximum or minimum is going to satisfy one of these two things. Doesn't guarantee it's a local maximum, but if I'm searching, those are my only candidates, which will be great. We'll get to that in a minute. Brooks. Mm-hmm. Is everybody okay with what we did here? All right. New definition. We're going to define a critical number for a function as any value c in the domain of the function, such that either f prime is equal to 0 or f prime doesn't exist. So this is basically my candidate list for my extrema. Just because those things are critical points doesn't guarantee they're extrema, but my only extrema can come from those critical points. At least if I'm on an open interval. If I'm on a closed interval, then I have a couple of additional places I have to check too. But these will be my only local extrema. Can come from that list. So let's take an example here. So let's say our function is f of x equals x to the 3/5 times 4 minus x. And I want to find the critical numbers for that, or the critical points. You could use those two terms interchangeably. I probably will. I don't need to confuse you. What should I do first if I'm looking for the critical numbers for this function? Take the derivative. Great. How do you want to do that? What's going to be the easiest route? Okay, you can absolutely do the product rule. Is that going to be the easiest route? Yeah, what if we just distributed it, right? If I do that, I have 4x to the 3/5 minus x to the 8/5. And do I need a product rule now? No. Wouldn't you rather do that than the product rule? Okay, what's the derivative of 4x to the 3/5? 12/5 x to the -2/5. Wonderful. Well done. And then the derivative of 8, or x to the 8/5. Great. Wonderful job. Well done. Now for the critical number, we're going to take that and set it equal to 0. How do I solve this equation for x? Factor. What are you factoring? Neither of them. I mean, one has an x to the -2/5, the other is an x to the 3/5. None of them have an x in it.
Wouldn't that be, like, just, I'm just correcting algebra, could 12 to the x to the negative, 12x times 12 over 5x to the -2/5, could that be 12 over 5 to the 2/5?
Sure. Does that help us? Does that help us any?
No, but I'm just making sure. Like,
Yes, that's 100%. That means
Okay.
the equivalent statement. For sure. Yes. 100%. Come on, guys. This is like an Algebra 2 question. You should be able to do this. I know. You're like, what? Definitely is. Do you need a hint? I would start by multiplying both sides by something. The reciprocal. There's lots of fractions. I'm not sure which reciprocal you mean. By 5? I mean, you can. That's not, I mean, I don't think that's going to do a whole lot. That doesn't make the problem really easier. What's the hard part about the problem? The fractions where? In the exponents. Well, if we multiply something to both sides, they're going to get rid of the fractions in the exponents.
Times 5 x to the 5th.
Well, if I multiply x to the 5th, when I multiply things with the same base, what do I do to their exponents? Add them. So -2/5 plus 1/5 still is a fraction up there. But you're close. It's really close. See it? Do you see it?
Oh. So would the 1 on the 8/5 become a 1,
Yeah.
and then the other one would cancel out?
Everybody see it? Now this is like some algebra 1 algebra here, right? What do we get? I'd have -12/5 times -5/8. You guys agree? What do I get?
6 over 4.
3/8. Everybody's okay? So that's one critical number. I have to check another thing though, right? The critical numbers where the derivative is 0 or where the derivative doesn't exist. Okay? So this is the equation for our derivative. What values of x are going to make this derivative undefined? Lucia already asked a really important question that's going to lead to the answer to this. You did a good job there earlier, Lucia. Asking the right question. What value of x would be a problem? 0. Everybody agree? You see it? That means 1 over x to the 2/5. You have 0 in the denominator. That's a problem, right? Is there any other values of x that are going to make this function undefined? I'm going to put a question mark next to it because we still have to check one more thing with that. But that's good. Any other values of x that would make this function undefined? Not sure? What does the fractional exponent mean? If you have x to like the n over n. Well, it means it's an nth root, right? The denominator is the index for the root. What kind of roots are these? Fifth roots, which is an odd root. Is there any problem taking the odd root of a number?
It's negative.
For an odd root? Right? So like, let's think for a second. If I do -1 cubed, I get a negative value back, right? So if I did the cube root of this, it should still get a negative value back, right? You can definitely do the odd root of negative values. Is everybody convinced? Where do I get problems, though, doing roots of negative numbers? For even roots. So square roots, fourth roots, sixth roots, those are a problem. You all feel okay? So this is the only thing. This is it. We found it. We got it. We do need to check one other thing, though. Just because it's undefined here doesn't necessarily make it a critical number. I have to check to make sure that it was still in the domain of f. So if I plug 0 into f, do I get an answer? What's 0 to the 3/5? 0. What's 0 times 4 minus 0? 0. Is that an answer? Yes. So what that tells me is that 0 is in the domain for f, but it's not in the domain for f prime. That's what I needed. So this is a critical number, right? If 0 was not in the domain of f, then it can't be in the domain of f prime because you had a discontinuity there anyway, right? Can't be a critical number for us because it has to be in the domain of f. So you do have that additional little check that you have to do after you identify the values in f prime that don't exist, or that make f prime not exist. You have to check to make sure that do those also make f not exist? Because if they do, they don't count. They have to still be a value, give you a value.
So what are you looking for when you plug your critical number into the equation?
So I'm just making sure I'm only doing it for this type. I don't care over here. Only here. And I'm just checking to make sure that I get a number to come out. Any number, as long as it's not undefined. Right? If I plug 0 into f and it comes out undefined also, it can't be a critical number. Because if we go back and look at the definition, a critical number of a function f is a number in the domain of f. If that number makes f undefined, it's not in the domain. So we have to check that one additional thing. And it's usually easier to go this route than like, I have to analyze the domain of f first, and then the domain of f prime, when if the domain of f prime is all real numbers, I don't need to do anything, right?
What did you write after that?
This,
Yeah.
that's f of 0. It's just messy. That's just me checking it to make sure that if I plug 0 into f, I get a number to come back.
Okay.
That's all I'm checking. And if it does, then that's a critical number. If it doesn't give me a number back, if it's undefined, it's not a critical number because that number is in the domain of f in the first place. So it wasn't going to be differentiable, but it can't be a potential location for a max or min because there's no point there. Is this okay? So this is the one that we want. If f has a local maximum or minimum at c, then c is a critical number for f. Okay? Doesn't work backwards. Just because c is a critical number doesn't make it a max or a min. But the only candidates for my local mins and maxes are my critical numbers. Lovely, right? That narrows down from infinitely many locations to a handful. They're relatively easy to find because all I have to do is solve the derivative equal to 0 and check where the derivative doesn't exist, which are two fairly Algebra 2 level tasks. Now, to this point, we've only been talking about local mins and maxes. What if I want to find the absolute mins and maxes? This is my method. So find the absolute mins and max of a continuous function on a closed interval. Find the values of the critical numbers. Find the values of the endpoints. Plug those back into the function. The biggest output, that's going to be my maximum. The smallest output, that's going to be my minimum. Done. It's okay to have a top. You just have more than one absolute min max. Ready to do an example? All right, our function is x cubed minus 3x squared plus 1, and it's on the closed interval from -1/2 to 4. The first step is to find the critical number, so we need the derivative. Great, what's the derivative of f?
3x squared minus 6x.
Wonderful. All right, let's find the critical numbers. So that's where the derivative is equal to 0. How do I solve 3x squared minus 6x equal to 0?
1x.
Okay, can we do a little better than that?
3x.
3x. Does it really matter that I just took out an x or a 3x? Not really.
So it's 0 and 2.
So my solutions are 0 and 2. Wonderful. Everybody good with that? We also have to check for critical numbers. Or is there any place where the derivative fails to exist? What type of function is the derivative?
Quadratic.
Quadratic, which is more generally called a polynomial, right? What do we know about the domains of polynomial function?
All the numbers.
All real numbers. Can the derivative fail to exist? No. So there's just none from this. Don't have to do much. Good, guys. Good so far? All right, so now we do our test. I need to test 4 values. My 2 critical numbers, my 2 endpoints. We'll see.
If you had a number from the
I would have to check that one too. Yep, because that's a critical number still.
Okay.
Right? Everybody's good so far? Start with that one, that's easy. Do that in my head. 8 minus 12 is -4, plus 1 is -3. do the full next. 64 minus 48 is 16, plus 1 is 17, I think. The negative 1/2, let's see, that's negative 1/8 plus 3/4 plus 1. So 1 plus, yeah, we do that. Or what's that, 13/8? Oh, that's going to be minus 3/4, right? Because the squared kills the negative sign. So 1 plus negative 3/4 is 1/4, minus 1/8 is 1/8.
How does the squared kill the negative sign? Doesn't it just connect to the x squared, not the 3?
I was talking about this negative. Negative 1/2 times negative 1/2 is positive 1/4.
Yeah, okay.
That was one. So what do we got here? So this is my absolute minimum is equal to negative 3, and it happens at x equals 2. Because that's the smallest number overall. My absolute maximum is 17, and then that happens at x equals 4. Does that feel okay? And again, this is something that, like, that's a reasonable no calculator problem, right? There's arithmetic at the end was a little bit rough, but like, the numbers were small enough that realistically you should be able to handle that. Even the fractions, I know. Next piece says use your graphing calculator to estimate the absolute max or min and max values of this function. We're not going to do that because you guys told me before that you already remembered how to do that. And quite frankly, I'm in the interest of like picking up time on that. Spending time. It's on the calculator. But part B says use calculus to find the exact minimum and maximum values, and that does interest me. So let's do that. What do I need to start with? Critical numbers, right? Okay. What do I need to start critical numbers? The derivative. What's the derivative of f? Did someone say cosine? You should have. Okay. Then what? Perfect. Okay. And then be positive 1/2 because you got to divide the negative 2.
Oh, yeah.
And then so x is cosine inverse of 1/2. All right. Unit circle experts, what quadrants is cosine inverse of 1/2 going to lie in? 1 and 4, right? Because cosine is which coordinate in the unit circle? X, and the x is positive in quadrants 1 and 4. Perfect. In quadrant 1, where's the x coordinate equal to 1/2? Pi over 3 is correct. Who didn't have that memorized still?
I did, it just was not my launcher.
Okay, so if you don't remember, you know that the x coordinate is 1/2 because it's cosine, correct? The y coordinate is root 3 over 2 because those 1/2 and root 3 over 2 are always paired together, correct?
It's positive. Everything's positive first.
Sure. Everybody good? 1/2 is 0.5. Root 3 over 2 is like 0.866. So if I graph that, my y is higher than my x, right? Everybody agree? So if I drew the standard position angle, it's the bigger of the two. It's pi over 6 or pi over 3. Which one is it? I'm 50-50 guessing. Well, it's the bigger one. It's pi over 3. So if you don't have those memorized, I never really had them memorized. I always just kind of like, which one do I need here? Like I have the pi over 4s, those are easy. Because they're just, anyway, that's, if you didn't remember. Okay, what's the fourth quadrant answer then? Once you have this one, it should be easy.
Negative
Okay, which is the same thing, but that's not in the fourth quadrant because it's not between 0 and 2 pi. So let's do coterminal to that. Well, 5 pi over 3?
Oh, so.
Because you got to go the other direction, right? Because you have to be between 0 and 2 pi.
Well, we have to memorize the second.
Should you know those? Yes. I don't see it happen a lot, but it is an expectation that you'd be able to do this on the AP exam if it were to come up. I don't think it comes up a lot. I wouldn't like stress out about it, but like you should be able to do unit circle trigonometry without a unit circle on the AP exam. I know,
Wait,
but I'm just being truthful to you.
is 5 pi over 3 the same as negative pi over 3?
Yes, if
So-
you just add 2 pi to it,
Why doesn't it work then?
negative pi over 3 isn't between 0 and 2 pi.
Oh, you gotta go.
Okay, so those are where we're equal to 0. What else do we have to check?
It doesn't really exist.
Okay. All right, where does 1 minus 2 cosine x not exist?
Isn't cosine of 0 1?
Cosine of 0 is 1.
So that's.
Huh? What'd you say?
It's great.
No.
It never doesn't exist.
Excellent. That's 100% right. Yes. Because what is the domain for both sine and cosine? All real numbers. Remember, what does the graph look like? Goes on forever in both directions, right? That's lovely. We love that. Give me all the derivatives where the domain is all real numbers. It's one less thing to worry about. All right, what do we need to check?
Like,
0. Pi over 3. 5 pi over 3. 2 pi. All right, let's start with the easy one, 0. When I plug 0 in, what do I get? 0 minus 2 sine 0.
2. Negative 2. So sine. Oh, sine.
Because we're in the F. It's 0. You're doing so good, though. Don't get frustrated. All right, let's go to 2 pi, because that's the other easy one. What's f of 2 pi? Two pi minus 2 sine 2 pi. Just 2 pi. Because sine of 2 pi is also 0.
Should we be able to like, do that in our head?
Yes. I know. Like, Mr. Kulik, that doesn't seem fair, but yes, that is the expectation. I know. Think about on the unit circle, though. 0 and 2 pi are coterminal, correct?
What does that
Means that they are at the same location.
mean? Oh, yeah.
So if you knew this one, you should know that one.
Okay.
Is that fair?
Sure.
Yeah, I know. All right. F of pi over 3. Let's write this one down. What's sine of pi over 3? Okay. Square root of 3 over 2. We just talked about it.
Yeah.
You didn't memorize
Yeah,
it?
I memorized it last year, but that was last year. Yeah, you have the answer memorized? Okay.
Can I combine those pi over 3 minus root 3? No. What can you tell me about that number, though? Is it going to be positive or negative? Good. How can you tell?
Because pi over 3, or root 3 is bigger than pi over 3. And it's -3.
Okay, pi over 3 is about what number? You'd estimate it. About 1, right? Pi is 3.14 divided by 3 to get just about 1. Square root of 3 is
0.860. Or no, over 2.
yeah,
So multiply that by 2.
it's about 1.7. Okay, so this will be a negative value, around negative 1.6, 1.7, negative 1.6, negative 1.7, something like that. I know. I shouldn't have said that. All right, let's do the next one. I'm going to shortcut all the way to here. Is everybody okay with me doing that?
So
Oops.
that is a positive.
Oops. Why is it negative? Root 3 over 2. Why isn't it positive?
Because it's in the.
Come on in, Maddie. Maybe you can answer.
Yeah,
Why
can
is
you help me?
why is the
Yeah,
negative
you-
square root of 3 over 2? Why is this negative?
Yeah, why is that negative? Is
We
it in the second quadrant?
Well, where's 5 pi over 3? Which
Fourth quadrant.
Fourth quadrant.
Yeah.
What is the value of sine in the fourth quadrant?
Negative.
That's 1.
I've
Okay.
been struggling today.
All right. Now here's the big question. We know this is less than 0, right? We just established that. So this is our absolute min. Everybody agree?
Yeah.
Because certainly 0 is bigger than that, or smaller than this, and this, right? Now the question is, which one of these two is bigger?
I'm gonna go on here and say.
No limbs. Tell me the answer and tell me why.
I don't
No
know.
limbs. You do. You do.
Well,
Which-
it's like it's in the fourth quadrant, and then 2 pi is like a little bit.
This one is the absolute max.
Yeah.
I
Why
was
is-
gonna say that.
You were right. I didn't want you to go on limbs though. Like I want to know why. Why is that the absolute max? Why do I know that's bigger than 2 pi?
Well, 5 pi over 3 is almost 2 pi.
Yeah. In fact, 5 pi over 3 plus pi over 3 is 2 pi, right?
Okay.
Which one of these two is bigger? Root 3. We just established that, right? Root 3 is about 1.6 or 7. Yeah.
Okay.
And then square or pi over 3 is
0.8.
about 1,
You're making our.
right? About 1. So this one is definitely bigger, right? Because 1.7 is bigger than 1.
Yeah.
Does that feel okay? Again, notice I didn't actually compute the decimals, right? I just know that, like, in fact, if I didn't know root 3 was 1.7, if I thought it was like 1.5, good enough. If I knew it was bigger than 1, good enough. I knew it was somewhere between 1 and 2, good enough, right? You see what I'm saying? Like, again, you should be able to do this, no calculator. I know, but this is why I'm modeling how to do this with no calculator. How to think about it. Is sometimes just an estimate is good enough, right? You gotta go back to like, in middle school geometry, pi was 3.14, good enough. Pi is 3, good enough, right? Root 3, I don't know, it's closer to 2 than 1. Because 2 square root of 4 is 2, square root of 1 is 1. 3 is closer to 4 than it is to 1. It's gotta be closer to 2 than it is to 1. I don't know. Somewhere in there. Bigger than 1.5. Who cares? Good enough. That'll work. Alright. I don't want to do this. Next section. In section 4.2, we're going to talk about the mean value theorem. Okay? Before we get to the mean value theorem, I want to introduce Rolle's theorem. This is not the theorem you've memorized by name or be expected to quote on the AP exam. In fact, it's only here to use to prove the mean value theorem, which I'm not going to prove in class because I'm looking to catch up on time, and that's like the explanation that I'm just not going to do. What Rolle's theorem says, if you have a function that satisfies these three conditions. It's continuous on a closed interval, differentiable on the open interval. The y-coordinate of the start and end are the same. Then there's some number in between the start and the end where the derivative is going to be 0. Emma? Sure. Is everybody okay? And this is an example of like, here's my A and B. If I try to connect this, no matter how I connect it, there's at least one place where the derivative is equal to 0, right? Because I can't draw a corner, because I have to be differentiable. I can't do like a vertical tangent or something, because it has to be differentiable. I can't pick up my pencil because it has to be continuous. Yes, Brooks?
This is such a dumb question, but can you take the derivative of just a completely straight horizontal line 0 over and over again, or can you just do it once?
Yeah, it's just 0.
Okay.
The second derivative is 0, third derivative is 0.
I didn't know if it was
Yeah.
like.
No, it's okay.
Okay. It was like undefined.
Right.
Take the derivative.
Okay. Let's look at a couple of things first, right? So what do you think we're going to do? How do we think we're going to prove that this has exactly one real root?
Just set it equals 0 and solve, right? Or at least take the derivative and then solve, and then you can find the real root.
So you could do this with the intermediate value, right? How would you do it with the intermediate value? Is that function continuous?
Yes.
Yes. How do you know it's continuous?
Um,
It's a polynomial. Perfect. Can you find a x-coordinate that gives you a negative y value? Give me an example of an x that gives you a negative y. How about 0? Right? If I plug 0 in for x, I get negative 1. Do you agree? Give me an x-coordinate that gives me a positive value. 2. I've satisfied the conditions for the intermediate value theorem, right? By the intermediate value theorem, there exists a value c on the interval from 0 to 2, such that f of c is equal to 0. Done. Everybody feel okay on that? That's how I would do that. No need to employ Rolle's theorem there. Mean value theorem. This guy is another one that you'll have to memorize. You'll be expected to be able to quote by name on the AP exam. You'll be able to list the conditions and the conclusion of the statement. So the mean value theorem states that let f be a function that satisfies the following hypotheses. Continuous on the closed interval. Differentiable on the open interval. If you have those two conditions, then you're guaranteed some value c such that the derivative of f at c is equal to the mean value for the function, i.e. the slope of for the start to the end. So like this is so like here is my mean value. Here's the slope of the derivative. Those two lines parallel. They have the same slope, right? So the average value, the mean value is equal to the slope of the tangent line. So the derivative is equal to, right? And now this value c need not be unique. So if I look at this function, here's the average or the mean value for the function. There's two places where the tangent line to the curve has the same slope. So again, this is a case where the c is not unique. There's two c's, p1 and p2 are both satisfy this. We're not proving the mean value theorem. Bye, Maddie. All right. It says consider the function x cubed minus x, and then from a to b. So this is just looks like that. So what can we say? Is this differential or continuous?
Yeah.
Why?
You take the derivative.
Because it's a polynomial. Is it differentiable on 0, 2?
Yes.
Yes. Why?
Because it's continuous.
Nope. Continuity doesn't guarantee differentiability
Because it's one.
because the derivative is a polynomial.
It's like a combination.
Okay. So we can then say there exists some c on the interval from 0 to 2 such that f prime of c is equal to f of 2 minus f of 0 over 2 minus 0. What is f of 2 equal to?
Is that x squared?
6. X cubed minus x. What's f of 0? 0. So this is 3, right? Okay. If I wanted to, then I could find that value of c. Because I know that f prime of c is equal to 3. So I just take my derivative for f. I guess I should make this. What's c going to equal? Three c squared minus 1 equal to 3. Plus or minus square root of 4/3, or plus or minus 2 over root 3. Is okay? What we did there? Just kind of showing you how I can use the mean value theorem to find the place on the derivative that has the same slope as the average for the mean value for the function. Okay. Suppose that f of 0 equals negative 3, and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Yeah, right? It's like, what do I do with this? This is, when you see how large can something be, probably it's going to be one of these value terms. Okay? Since we're given information about the derivative being less than or equal to, you probably want to use the mean value theorem. So let's try setting that up. Okay, what two conditions do I need for the mean value theorem? I need continuities on f. So how do I know f is continuous?
Because it's, you can take the derivative.
So since f prime of x is less than or equal to 0 for all x, f is differentiable for all x. So, what can I say with that? Okay, if I get differentiability, what do I get? Continuity for free. Differentiability implies continuity. So f is continuous for all x. Those are my two conditions I need for the mean value there, right? Is it okay that I didn't define a closed and open interval here? Yeah, because I have it for everything, right? You know, you place a for all x, you could say, you know. Right. That's the same thing. Everybody's okay? So, by the mean value theorem, we have that f prime of x, or f prime of c, is equal to f of 2 minus f of 0 over 2 minus 0. Why 2 and 0? Yeah, because I want to know about f of 2, and I have f of 0. Everybody agree? Okay, so f of 2 I want to know about. F of 0 is -3. And then I know that this guy has to be less than or equal to 5. So I know that 5 is greater than or equal to f of 2 plus 3 over 2. And now it is algebra time. Absolutely. What do I get for f of 2?
7.
F of 2 has to be less than or equal to 7. So what is the maximum value that f of 2 can have? Yeah. So again, you looked at that and you're like, how in the world am I going to do this? Knowing which tool to choose, and the problem is not anything worse than like an algebra 2. The hard part is reading that and going, value, let's do that. And the reason I knew to use that is because it gives me, it's the only one of those that's going to relate the derivative to the function, right? Extreme value theorem says the derivative equals 0. That's not going to help me. Intermediate value theorem doesn't give me any information about the derivative. The mean value theorem is the one that links values on the derivative with values in the function. So if I ever have to compare those two things, that's a mean value theorem problem. Does that make sense as to how I would know to choose that in the future? I think this is the last derivative theorem that you'd have to pull. Intermediate value theorem, extreme value theorem, mean value theorem are like the big three. Now there's integral ones later, but like it's usually pretty clear when you need to use a derivative versus an integral. We can talk about integrals, it's okay. Second semester.
Is that the opposite of derivative?
It is. It's like the inverse relation. Yeah. So you're like building recovering the derivative, or recovering the function from its derivative. Yeah. It's bad.
I feel like we could do that.
Yeah, it's not bad. I mean, in reality, like integration much harder than differentiation. But like practical purpose for what we're doing, it's easy.
Isn't it like, I don't know anything about it. Isn't it just like the area or the like?
It is related to areas. Let's focus back on this though.
Okay.
That's okay. No, you're on it.
I'm so excited.
I know, right? If the derivative is equal to 0 for all x on the interval, then the function is a constant function on the interval. Who is surprised by this result?
No.
Should be none of us, right? We've already established this idea that the function is a constant function if it's flat. Its slope is 0, so the derivative is 0. A similar result that's not unrelated to integration that we'll do later on says if f prime is equal to g prime for all x on an interval, then f minus g is a constant function, i.e. that f of x is just equal to g of x plus some constant. So what we're saying is that like if f of x, or sorry, if g of x is equal to f of x and say they're both equal to 2x, then f of x could have been x squared and g of x could have been some like x squared plus 1. Because when I take the derivative of x squared, I get 2x. When I take the derivative of x squared plus 1, I get 2x. Oh my gosh. Could they have both been x squared? Yep, still works, right? Because f minus g equals 0, 0 is still a constant. And we're not going to do this because I'm not interested in that, because it's more than we need to be worried about. I think after 2 sections, you guys are probably pretty cooked, and I should stop. Was today okay? Notice that the calculus parts here were really easy, right? Like taking the derivatives of the things that we're taking derivatives of were really easy. The hard part on these sections is going to be like understanding what I need to do. How am I going to use the derivative as a tool to answer the question? That's going to be, the derivatives themselves will start becoming easy. But what am I doing with this will be the hard part now. Even maybe the algebra being the hard part, like how do I solve for x equal to, f prime of x equal to 0 will probably be harder than doing the derivative. What do you guys think? So there are 2 homework sections for 4.1 and 4.2. When should these be due?
Next Sunday.
I don't even want to do them next Sunday. You guys don't do anything over break. Have them do this the Sunday after we get back.
Okay.
Okay? Like you worry about like your 100 IAs that you still need to do, or like whatever final exam project. You worry about that stuff. You don't have to worry about this right now.
Okay.
Is there IB math last class? That class, is there math due this Sunday?
Me too.
Yeah.
Fair? And you guys feel good? How was today? Was this okay?
It was good. I don't feel like I'm gonna.
This was real conceptual and not very
This wasn't that bad.
grindy
I
though.
feel like the last, like, before the related was like so much harder.
Oh yes. Oh yes. This gets harder, but we're just like dipping our toes.
Yeah.
This eventually ends in optimization, which you guys will hate.
What is optimization like?
No, it's like so like say I want to build the cheapest possible vessel to hold this much
Well, we
food.
know more.
What are the
I
dimensions?
know like the 1,000
For this vessel.
I think they're running something they call heroes.
You would be like all the same.
So it becomes complicated.
Wait.
Like I have this job that requires workers, and I have to pay the workers this much, and the job pays this much. And this amount of time the worker takes per worker to do the job or whatever. Like, what's the cheapest way for me to deploy my workers to maximize my profit?
Oh my god.
So optimization is like the most useful thing.
Euchre is really
the
difficult.
entire
I've
course.
never played Euchre.
Oh yeah, thank you.
But
I
it's
see euchre.
it's hard
You don't know euchre?
No, I
Once
played
you get it
more.
down, like.
because it's
I
abstract.
learned it once and forgot.
Because you have to like define what the problem is. You're not given like it's kind of similar to the related rates. It feels like I don't know what to do with
Okay,
this.
but not like if you're broke.
What even is it? It's a card game, right?
Well, typically it's that first semester.
Yeah.
Like, I don't really know what to
Kind
do
of game
with this.
where?
Okay.
Yeah,
Iraq.
that's
I
what I thought.
swear.
Iraq.
So you had to think about it. You had to think about